Okay, we'll go ahead and get started. People can trickle in as they like. I'll start out with some basic introduction stuff. Welcome, everybody. I trust you can hear me. If not, please speak up. Or sometimes my audio goes out. I haven't restarted my computer in about 5 days here, but so far this morning, the internet's working well. Everything's looking good. So hopefully we won't have technical challenges today. Yeah, great to be here with you to talk about working with CalAdapt climate data in R. So I put the link to the slides, to this workshop materials in the chat window. I just put it in there again. If additional people trickle in, maybe somebody could add that a couple more times. So hopefully everybody got the welcome letter and you're here. So obviously you got the calendar invite. Hopefully everybody got made progress on installing the packages that we'll be using today for the hands-on exercises, and or set up an RStudio Cloud account and clicked on the link that I sent last night to a RStudio Cloud project. And that's what we'll be using today. That's what I'll be using for the demos. I will pause, not right now, go in a little bit, see if there are any quick setup questions, but we're pretty much just going to plow ahead. If you struggled to install anything, don't worry. This is only an hour workshop. All of the notebooks and stuff, I'm going to talk through them, and they're online, so you won't miss out too much. If you just need to watch, and that's fine as well. Okay, so let me go to the first set of slides. All right, great. Glad you got it. Okay, so a little bit about myself. So I work for the University of California. I'm based on the Berkeley campus, but I actually don't work for the Berkeley campus. I don't teach, I'm not faculty. I work for the Division of Ag and Natural Resources, which is one arm of the UC system. I love it. It's a great branch to be part of. It's very, very applied. We are the division of UC that does applied research throughout the entire state of California. Those little purple dots, we have offices in all of the counties in California with one exception. We have 9 field stations. We have clusters of faculty on 5 of the campuses. And this is the branch of the UC system that does research and training and extension in the domain of agriculture, natural resources, and food systems. So it's really wonderful. And there's a bunch of statewide programs. I work for the Informatics and GIS statewide program. That's a GIS group that supports this whole network. So that's a little bit about me. I won't go into our background too much. But I would like to acknowledge some other important people who have been part of this project. Big thanks to everyone at the CalAdapt team, especially Brian Gailey. He's kind of like the chief developer behind the API. He's been very patient answering my emails. I think I've only crashed the API once or twice. Lucy, Eric, Shruti, Nancy Thomas, the director of the Geospatial Innovation Facility, which is they have built CalAdapt and support it. My colleague Shane Fire and Maggie Kelly from IGIS, and then the main funding agencies behind this are the California Strategic Growth Council and, of course, the Energy Commission. So thanks to everyone for making this big project work. So a little bit about you guys, or at least the people who registered. So heavy academic organization slant here. So roughly 50 of you are coming from academic institutions, and then a healthy chunk from state government agencies. So thank you everyone for coming for that. And then a hodgepodge of other types of organizations. A lot of you folks are from agriculture and natural resources, which is expected given the audience and given what we're doing today, but lots of other fields of work. So really great to see a diversity of interest in working with climate data. This is quite normal. It's the thing of our age. A lot of people who are somewhat or very familiar with R, that's wonderful. So I will be going through fairly quickly, but most of the code is kind of ready to go. So if you're not super familiar with R, don't worry about that. I'll talk through it when we get to the code section. Even if you're a complete beginner, you should be able to hopefully get something to show up. And many people here are familiar with climate data, either somewhat or very familiar. So that's great. This is something we're all learning. Unless you've just been in school recently, you probably are like the rest of us and kind of learning about climate science as you go, right? Because this is what we have to deal with in our work. All right. Okay, so what are we going to do today? It's a relatively short period of time, but we're going to try to, my goal is broadly to get you familiar with what you can do with caladaptR. This is the package that I've been working on that helps you get data from caladapt into the R environment. And even though if you don't remember all of the details, you can at least have a broad familiarity. You'll be able to go back to this material when you need it to get caladapt data into R and start playing with it. We will do some hands-on practice with the code. So we got some R notebooks lined up. Fingers crossed that'll all work. But basically, the main thing the package does, it gets caladapt data into R as tables or rasters. And then R is super powerful, and we're going to look at different ways that you can wrangle or munge those tables for making plots or other kinds of visualizations, right? So the bulk of the work is actually not going to be working with getting the data in there. That's relatively easy. It's what you do after that. And I will show you a few techniques of working with large volumes of data because climate data are large. And there's a lot of applications for it out there. So those are the main goals. My secret goal, though, is really to hopefully get some more people using caladaptR because when I've learned so much from people who are interested in working with climate data in R. So every time I can learn of a use case for an analysis or visualization, those ideas become code recipes, they become new features for the package, they become documentation. So that's an open invitation for everyone to stay in touch and let me know how I can help you get through your work. The strategy today is going to be really focusing on code recipes. This is I think a lot of people who use R, nobody tries to memorize every function that you're going to need. A lot of us will just kind of like understand the basics, the basic concepts, but really put together code recipes that we can go back to and have working examples and a bit of practice so that we can kind of mix and match what we need and get functional in R. Okay, so it's going to be the output of today. Whether or not you've learned as much as you want, you should definitely have some functioning code notebooks that you can come back to. Okay. Okay, so that's kind of like what we're hoping to do in the workshop. So what is caladapt? I think everyone here is probably familiar and knows that caladapt is California's official portal. It is state sanctioned. It's been developed by the state. This is all peer-reviewed climate data. Almost all of the data sets are downscaled climate data. So that's going from the 100 kilometer pixels from the global climate models and downscaling them through the LOCA method to more like 6 kilometers in pixels, in pixel size, right? So the data sets have been selected through the 4th climate change assessment, which is a state-driven process with lots of science panels and lots of researchers. And here are some of the main data sets. The big ones are certainly going to be your modeled climate data. That's both the future as well as historic modeled climate variables, such as temperature, such as precipitation, and so forth. There's also a number of derived variables, things like humidity and solar radiation that also take into extent land cover types, and so on and so forth. So it's a really rich set of data. 950 raster layers are actually in the API right now, which is pretty amazing. This link here is a nice is a newish kind of table on the new caladapt website that actually provides a nice summary of some of the main data sets that are available, including the institutions they came from. So that's good to see. The extent of caladapt data. A lot of people don't realize it actually covers all of Nevada and a good bit of the surrounding states. So keep that in mind. California is fully covered for all of those downscaled climate layers. And these are the main agencies who have supported development of CalAdapt in the API, and all of this came out of the fourth climate change assessment. I know there are a lot of climate experts on the call, so if I do misspeak or gloss over anything, please chime in the chat window, and we'll make sure we get the corrections. Okay, so but where exactly are these data? That's a good question, right? Most of us are familiar with the CalAdapt website. There's a dozen or more really well-designed interactive tools and some maps that have been well-developed and vetted. But let's step back first. All of the data originate through science researchers. And there's 32 groups around the globe that have developed the global climate models. There's groups within the United States who take those climate data and do other things with them, come up with derived variables. So California's fourth climate change assessment organized and vetted all that. And then CalAdapt is kind of the institutional host for these vetted science layers. So they do have one server on site. I believe it's on the UC Berkeley campus, where all of the source data can be downloaded through FTP. That's known as the CalAdapt data server. But they also have copies of a lot of those layers in the cloud on Amazon hardware. And that's what feeds the API, right? So the API is kind of like a language that the computers all understand. And the CalAdapt data can be sent to other computers via this API. That includes all of the tools on the website. They get their data through the API. But it's an open API, it's well documented. And the work that I've done here and my colleague Shane Fire has done is to create program bridges so that you don't need to know all of the weeds of the API, like how to parse JSON queries and that kind of stuff. We've written functions in R and Python that kind of do that translation, that serve as a bridge from the data to other platforms, such as R and Shiny, which is an R package, as well as Python, and by extension, ArcGIS Pro, right? So these bridges, that's the new stuff that we've developed over the last year. Okay, so there are a variety of ways that you can get to the data from CalAdapt. The website pretty much makes everything available. That FTP server, you can get the source files as large netCDF files, like lots and lots of them, but it's open. It's an open FTP server. The CalAdapt Python library will allow you to get the statewide rasters. You can query your own area of interest, maybe a watershed or something like that. There's 10 recommended GCMs for the state of California available through the API. And then all 32 GCMs are not on the API. There are ensemble runs, but if you need the individual source data, you can use the FTP server or Shane's Python libraries. You can also query features. That's where you don't want a raster, but you just want a table of values for a specific point or a specific polygon and so forth, right? So the CalAdapt package does that for Python. The preset boundary layers. So these are kind of like pre-chugged layers such as census tracts and county boundaries and congressional districts and watersheds and so forth. So those are already built into the API. And the advantage of using a boundary layer is that you don't actually need to pass it a polygon geom or shapefile or something like that. You can just use the right syntax and get the values you want for one of those predefined preset areas. So you can see what the caladaptR package does. It does most of this with the exception of getting the all 32 GCMs. I've not built in any functionality to grab the netCDF files from the FTP server, at least not right now. There's a really nice webinar here that you can look at to learn more about CalAdapt climate data. Okay. So, but why might you want to even work with CalAdapt data in R? And that's a good question. Because there's great tools on the website. You can download the CSV files from the website and so forth. So R is really good. It has a lot of custom visualization packages, plotting libraries, mapping packages, and so forth. So what you might need some customization in how you're visualizing the climate data. You may also want to integrate climate data with other kinds of data, right? So census data or biodiversity habitat, niche models or economic data and so forth. And R is a solid, hands down data science package, and you can do lots and lots of data manipulations and analyses within R. So by getting the CalAdapt data in R, maybe as a data frame, then you can join it with some of these other kinds of data that you have and do your work. The R has thousands and thousands of packages. Many of them, are, tailored towards these kinds of analyses. Some of them are tailored towards like climate stuff, like, there's growth models and, chill hours and growing degree days and stuff, right? You can also run your own models, right? So you may be doing something new, a new way to compute like heat impact, or some new way to compute runoff or something like that. R is a good platform for doing that kind of research, that kind of low-level testing out stuff. R is also pretty strong for decision support, not just the statistics and the summaries, but actually you can create, as we shall see today, lightweight online graphical decision support tools with R Shiny. And you can use CalAdapt data in those through this R package. So there's a lot you can do in R. It's a good package. So what does this package actually do? So caladaptR is a very classic API client. It does one thing and one thing only, and that's to help you get data into, in this case, R. We'll see how you construct an API request and then use that API request to fetch data. So this little gray box represents what the package does. And then once that's done, then you turn to other libraries, other packages to do what you need to do next. Maybe wrangle the data, analyze it, and so forth, right? So the package itself really only does one small thing, but that's an important thing, is getting data into R as painlessly as possible. Okay, so it can do querying, it can import data. It's a very new package. It's just coming out of the oven here. As we'll see, it's pipe friendly. If you use the tidyverse, this is going to look familiar to you. It's using most of the modern data classes, Tibbles, SF, stars. That's a spatiotemporal arrays, so kind of a higher dimensional rasters. It's using the units package to see what the units are for the results you get back, and so on and so forth. So mostly you can use it to you can query any of the 949 CalAdapt raster series through that are available through the API, and they're adding more every few months. You can either use your own geomes, your own points or polygons, or you can use one of the preset layers, and you get data back as Tibbles or as stars objects or TIFFs that you've downloaded. The package it's not going to teach you how to work with climate data, right? It's not going to teach you how to work with data in R, right? So those things you need to know coming into it. There is a bit of a caveat though, because you have access to all of this source data, and you need to know how to use climate data wisely, right? You can, in fact, drill down and find out what's the projected, precipitation for the month of August in 2079 in some location. That's not a wise use of climate data, but that's the kind of level of detail that you can get by having access to the source data through the API. Okay, please pause me if there are any questions, otherwise I will just keep on going here. So to use the package in R, there's basically 5 steps. First of all, you need to think about what is your location of interest. That might be the whole state. Quite often now, it's smaller than that. So you have to think about what that is, and how are you going to specify that? Do you have your own polygon layer, or can you use one of the built-in preset areas? or maybe just a set of points. Once you know that, you're going to create an API request object. You're going to string together a set of functions that will collectively define what is the data you want. It's kind of like filling in an order form. You take that API request object and you feed it into a function that actually fetches data, right? Either as tables or as rasters. Then you get back that, and then your next step is to start munging that, playing with it. You may have to subset, you may have to do some grouping, depending what you're trying to get done, and then you keep going on with your work, right? Okay, so in broad terms, that's how it goes. So here's a quick little example. So we load the package as you always do. This box 2 under 2, this is defining an API request object. And as you can see, it's a set of functions that collectively provide all of the pieces of the API request, the data that you want to get back. The dates, the climate variables, the global climate models, and so forth. We'll see examples of this shortly. And these are all just strung together with pipe characters, right? So hopefully everybody's familiar with the pipe operators. Okay, then typically before you issue, you send that request to get data, you're probably going to just check it out. You can just type the name of it and it'll show you what's in your API request. There's a function called preflight that will actually do some checks, make sure that the location is actually in the coverage area and that you haven't put in anything that's, there's an actual data set that you want. The package does have a copy of the caladaptR data catalog, right? So it does a quick check there. You can plot your API request and it'll show it on a little interactive map. And then you can even see what are the grid cells, the local grid cells, so 6 kilometer grid cells around it. So you can see how many of those it's going to have to get. Then you take that API request object and you feed it into a function that fetches data. And there's 3 of those. This is the one that gives you back a table, a tibble, which is like a data frame. And then this is what you get back. You get back a standard tibble, may have lots and lots of rows, and you can see at the end there are going to be the values of what you're getting back. Right? In this case, we're getting maximum daily temperature. That's average per year. Right? That's how it's requested. Okay, so that's the essence of it. I'll just talk about a couple more general features, and then we'll go into one of the notebooks. If you do want to get lots and lots of data, so for example, every census tract in the count in the state of California, there's over 8,000 of those. Maybe you want daily temperature data. That's going to take a while. You can do it. There's a special function for that kind of large query. It ends with _DB, that stands for database, because what this function does is under the hood, as the data is coming down, it's throwing it into an SQLite database, which it makes on the fly and manages for you. So this is a good way, if you do have lots of data that you need to get, by putting it into the SQLite database, then you don't have to download it a second time. If your internet connection is slow, it just kind of manages it in the background. If it gets disconnected, you can just pick up where you left off. And at the end of all of this, you do get a remote tibble. So you do get something which is like a regular tibble or data frame, but it's remote, meaning it's actually a pointer to that SQLite database. So you're not slowing down R with you're not using all the memory for your R. Yeah, so there's a whole vignette or article on working with this function and working with SQLite databases as part of the package. And there's an R notebook that we'll see as well. If you do want to get rasters back, there's another, you feed your API request object into this function, get rasters _stars. And what this is going to do, it's going to get those same data layers and it's going to download them as a bunch of TIFFs, right? So you tell it where you want those TIFFs to go. They come in as TIFFs. Now, TIFF is not a great file format for this kind of data. It's basically limited to 3 dimensions, but the function will actually save some of the additional metadata, such as what date does each layer in the TIFF represent. That gets saved into a sidecar file, which is a little tiny text file that has those additional information that lives next to the TIFFs. And then you can read those TIFFs back into R with a function called read stars, and that brings them into R as stars. So stars are, they're like rasters, but they can be higher dimensional. They can be n-dimensional, which is helpful because with this kind of data. So you might have multiple TIFFs, and if you want, you can combine those into a single 6-dimensional stars object, where those higher dimensions represent the, your GCM or your scenario or what the climate variable is. And you might wonder, well, doesn't that seem overly complicated? But if you know how to use stars, stars is a great package. It's relatively new, and it really does a nice job of dealing with like multi-dimensional spatiotemporal array. And that's the name of the package. That's what it's designed for. Anyway, there's a couple big nets that describe how to go through that. If you do have a large geome, such as the entire state of California, right? The API will not give you back a raster for the whole state of California. That's too big. There is an upper limit on it. But what you can do, there's a function that will take that large geome, chop it up into smaller blocks. Then for those blocks, you feed those blocks into this function up here, and that'll give you a bunch of TIFFs. And then you read, and then you can mosaic them together. There's another function that will mosaic those. So in other words, it's a bit of a workaround, but at the end of the day, it's a way of getting raster data for large areas. And then you get back a stars object. Yeah, so stars is a newish package. I don't think we have time to get into any depth here, but it supports dplyr style filtering, so you can use your filter functions, your select functions from dplyr. Those work with stars objects to get just the dates or just the rows and columns that you want. And you can do things, all your classic raster operations, raster algebra. The cool thing is that you can do pixel summaries, right? So you might, for one pixel, you might have multiple GCMs, multiple emission scenarios, and you can write a custom function that takes all of that and spits out whatever the summary that you're trying to get, right? So there's a stapply function that you can use a custom function. And of course, it can do reprojections and splitting and then some basic plotting, right? So there's 3 big nets on working with rasters on the R package. So the raster functionality is relatively newish. So if anyone out there is keen on working with the climate data in these raster formats, I would love feedback, and I'd love to see what you're doing and help out if I can to piece these functions together to get your work done. Last thing is Shiny apps. So Shiny apps are an online version of that you can package your R data into, and there's a couple Shiny apps. I'll just see what one looks like. So basically, they're lightweight web apps that you can use to present your R work to people who don't use R, because the biggest problem with R is that it's got a high learning curve. So here's an example of, you can select the location on your map, pick your date ranges, pick your climate variable, pick your GCMs, your emission scenario, and then clicking this little button here is actually going to fetch from caladaptR. See how quick that was? And this is just annual data. But basically, under the hood, under the engine here, we're using the caladaptR package to fetch data based on the settings of these user interface controls. So that's Shiny, and that's a really good way to create customized decision support tools for your users. There's a couple of those on the website. There's actually a whole package called caladaptr.apps, and that has them built in. And there's an R notebook here, if we get to those, where you can run some of those. Okay. So Okay, I'll keep going. I'm keeping an eye here on the chat window, so please chime in if anything comes up. I know a lot of you folks might be Python people. Python is probably a more common language or programming environment, certainly among the GIS world. My colleague Shane Fire has developed the Python library I mentioned before. He's going to give a workshop on that later this fall or maybe early 2022, but soon. You can use the functions that he's built in his Python library in Jupyter Notebooks. And he also has developed an ArcGIS Pro toolbox, which presents a nice little menu for, again, importing data from CalAdapt, both the netCDF files as well as through the API. And then once you get them into ArcGIS Pro is a ridiculously powerful platform for spatial analysis and all kinds of visualizations. This is one of the new ones. It's a 3D spatiotemporal voxel. Can't even put my head around that, but you can do a lot with ArcGIS Pro, as you might imagine. So keep an eye out for the workshop from Shane. He is also looking for people to help him test his work and continue to improve it. Okay, so here are some resources for working with this package. The website is the main place to go. That's where the documentation is. There's 5 articles. I got 1 or 2 more in my kind of in the pipeline. I'm trying to create more and more R notebooks, just kind of like code recipe samples. So there's some there. There's some new ones for today's workshop that we'll see soon. There's some presentations there. Some things I'm still working on for the rest of this year, putting together an R package for growing degree days. There's like 9 different ways that you can compute growing degree days. So there'll be an R package that'll make those easy to do. Working with weather APIs. We'll be doing another version of this workshop coming up sometime later this year or early 2022. And I've got some more Shiny App projects that I'm working on. So, but as mentioned before, I would love to find out, what people are working on and getting code recipes. I mean, the niche of working with CalAdapt climate data in R is really tailoring analyses and tools and visualizations to very specific use cases, because climate data in general and CalAdapt it's like a fire hose of data, right? And many people can't put our heads around that. So R gives you a way to kind of customize it and tailor it and make it more streamlined for your use case. Okay, questions? Okay, we're going to go to the notebooks next. Notebooks, I assume most of you have worked with RStudio. Probably most of you have worked with R Markdown files. R notebooks are a flavor of R Markdown. They're not one of the more common ones. I like them for workshops though, because you can actually run through them. So as we get to the interface, basically, if you've worked with any kind of R Markdown, this will all look very familiar. It's plain text. There's some Markdown characters that when you preview this as an HTML page, these will be turned into character formatting. The code itself is in these code chunks, so these gray boxes. And to run code in a code chunk in our notebook, you simply click anywhere. You can run them line by line. So you just click on that line and then you can click the run button or hit Control Enter. If you want to run an entire code chunk, you can just click anywhere inside that code chunk and click that little green arrow, or I think it's Control Shift Enter. Right. So that's what we're going to do. We're going to go through these. Something that's unusual about or different about our notebooks is that the output of code that you run in these code chunks by default appears underneath the code chunk, like within the notebook, right? So that's takes a little getting used to if you're used to seeing things pop up in the console or in the plot window. But the nice thing is once you're done with all that, you simply save your notebook, click the save button, and then wait a second and then click the preview button. And everything that you've run to date will pop up in the nicely formatted HTML file, right? So it's a good way to kind of like do your work and then save it. This is not the same as knitting, right? So it's not going to run, when you click that preview button, it's only going to render in HTML the code that you've run. If you haven't run some code chunks, they're not going to, you won't see anything there, all right? So that's what we're going to do next. All right, any questions? Okay, so go fire up RStudio or RStudio Cloud. And I got my RStudio Cloud running. And what I did was I clicked on that link that I emailed to everybody last night. And then I make sure you click the save permanent copy so that that project gets saved into your RStudio Cloud workspace. Right? This will all work also if you follow the setup instructions for installing all the packages in the RStudio desktop. And then I also sent get rid of this stuff. I sent a command to download into RStudio desktop all of these files that we see right here. So this is all the workshop files. The slides that we were just looking at, they're not yet here, but I'll add them to that zip file after this. Okay, so let's go ahead and go into the notebook. So assuming this is all working, if not, you might just want to watch, but go and click on the notebooks folder. So I've got my files pane open in RStudio. That's the files pane is over here on the lower right. And then click into the notebooks folder and then open up the first notebook. So that's nb01_intro.rmd. Okay, so you click on that and then it opens up in RStudio Cloud in your Windows. Okay, so this first notebook, we're just going to get going with this and try to get our and yeah, we'll just do some basic running of this. Okay, so I'm going to come down here. You can read that intro material, but the first thing we're going to do in code chunk 1, right? So I'm assuming that right now a lot of you probably are looking at RStudio Cloud. You're not looking at my screen share, which is fine. So I will try as much as possible to describe going through this notebook, right? So come down to line 29. That's code chunk 1. And I'm gonna run all of the commands in code chunk 1 by pressing Control-Shift-Enter on my keyboard here. So you click inside the code chunk. You can also click that green arrow. And if everything worked out, you didn't get any error messages, then all of the libraries are now loaded. This code chunk doesn't provide any output, so there's nothing that appears below it. Next, coming down to code chunk number 2. Go ahead and just click in there, and then again, Control-Shift-Enter. Now let's take a look at what's going on here. So this is a command that's constructing an API request object. And you should be able to kind of like follow how it's working. The first function there is defining the location, right? So we have to say what location we're interested in. It's using a function that will accept point coordinates. So we're getting climate data for a specific point location. Then there's another function that tells it what are the GCMs that we want to use. It was actually a constant that we'll look at in a second that has all of the 10 GCMs. So you don't have to memorize those funny names. You can use that constant. And here we're taking the first 4, which are the 4 priority models for California, defined by the 4th climate change assessment, and so on and so forth, right? So the next function defines the emission scenarios, what temporal aggregation period. So the choices there will be, normally it's day or year. Some of the climate variables have also been aggregated by month. That varies a little bit. And then the years, and then of course we have to specify what climate variables do we want. In this case, we're getting the minimum daily temperature and maximum daily temperature. So go ahead and run that. And nothing appears. All we're doing is defining that project, that one. Pro tips, the order of the constructor functions doesn't matter. Please remember that if you are entering your location by a specific point, you need to put those in as longitude, comma, latitude in decimal degrees, and so on and so forth. Okay. So code chunk number 3, this is where you get to type in something here. Basically, there are some constants that come with the package that help you construct your API requests. There's one for the GCMs, the scenario. So just go ahead and in chunk number 3, type in the word GCMs and hit enter, right? And you will see that's a constant, right? So you'll see what the GCMs are. And again, those first 4 are for the priority models. And then likewise for scenarios, hit enter. And then CVARs, those are your climate variables. And then these should all look familiar. And then periods are going to be your temporal aggregation. So you can use these constants to help you kind of know like what are valid values that you can pass to those functions to build your API request. Okay, so I see a message here in the chat window from Laura saying that she's getting an error message that caladaptR is not available. That sounds like a setup issue. And that message that says it's not available for your version of R, that just means it's not available at all the way you're trying to load it. So go back to the setup page and instructions on the website and try that again. And I can help you, Laura. Not right now, but maybe after the workshop to help get that installed. Okay. Okay, continuing down. Okay, so we've just seen, the constants for the various climate variables, snow water equivalent, precipitation, and so forth. It's worth noting that not every climate variable is going to be available for every GCM and scenario and period, right? So those are the options, but it doesn't mean like any combination of those is going to work. We will see further down how you can see what combinations are actually available. Okay, so I'm now in chunk number 4. So go ahead and run that. And here we are simply plotting, or we're simply entering the name of the API request object that we created, and it's showing us what's in there. Okay, coming back. That all looks good. You see the location. Chunk number 5 is a kind of a convenience function. If you want to kind of tweak the way your the way the colors of the various output appear, you can see it. There's a function called CA settings, and there's a couple of color palettes. You can also specify your own. So depending if you have if your RStudio background is white or dark blue, there's like a bunch of different options you can pick from. You can pick with one of those. Okay, so moving down. Chunk number 6 is where we're going to run the pre-flight function. So there we're basically, it's just going to check whether there's any issues with that API request. We still haven't tried to get any data with it yet. We're just seeing what's there and looking at it. Chunk number 7, go ahead and run chunk number 7. Hopefully, if that's working, you should see a map pop up below that chunk. It's a little leaflet map, and you can see the red dot indicates the location of your API request. Okay. So chunk number 8 is doing the exact same thing, but now the chunk number 8, we're using another argument in the plot function, loca grid equals true. And what that will do is it'll overlay the local grid cells. So like, maybe you're doing like a polygon area and you want to say, okay, well, how many grid cells does this cover? That can help you just kind of see how big is your area relative to the local grid cells. Okay. Yeah, so Meredith is seeing an error. That pops up occasionally, Meredith, that I'm getting an error, HTML dependency not found. What you could do there, if you go to preview and then clear your knitter cache, that usually fixes that. I don't fully understand that error. It's generally not a showstopper. And that generally will come up when you click the preview button to preview your notebook. Yeah, that's a gotcha. Okay, I'm going to come down to code chunk number 9, right? So let's actually get some data. We haven't done this yet. So code chunk number 9, as you can see, we're taking that API request and we're piping it into the get vals function. And when you run that, you should see a little progress bar, and it's actually communicating with the caladaptR server and returning the results. And then if the head function in there will actually show us what came back. All right, so we have the, in fact, if you type the name of the tibble, pt1_tibble by itself, without that head function, I can see there are 816 rows that it just retrieved in 8 columns of data, the last one being the temperature for Tasman and Tasman. Okay, so that's a general example of getting data in a tabular format based on a location query, right? So you kind of get the idea. Chunk number 10, we're simply using some dplyr functions. Go ahead and run all of chunk number 10. So just double or click in there and Control-Shift-Enter to run them all at once. You may or may not be familiar with dplyr, but you can kind of see what it's doing. It's doing a subset based on, now we're only pulling out RCP 4.5 and we're only pulling out TASMAX, maximum daily temperature, and we're adding a new column, converting the temperature values from Kelvin to Fahrenheit using the set units function from the units package, which is possible because the units are saved there. Okay, so that's a little example of how you can use dplyr functions. Probably most of your work is going to be using that kind of dplyr function. It's not that hard to get the data in. It's what you do next with it. Chunk number 11, go ahead and run that. It's just, this is ggplot, standard ggplot stuff, and it's creating a line series graph of the temperature values for the, grouping the various values into by GCM. Okay, ggplot is insanely powerful. I have to Google almost every time, but nonetheless, you can do lots and lots of cool stuff with ggplot. Okay, chunk 12, what's that? Okay, that's where you can do on your own. I'm going to keep going here just so we cover a little bit more. Think about how could you take how could you modify what we just did and only get RCP 8.5, right? And then there's a little bit.ly link there. If you hit Shift and then the mouse and click on that bit.ly link, it'll open up in a new browser window. Okay, questions? Pause for. Okay, let's go to part 2. So part 2, it's going to be pretty similar, but in this example, instead of using a point location, we're going to use one of those preset area of interest, one of those boundary layers, and we're going to grab data for an entire county. Okay, so coming down here, let's go to chunk number 13. So chunk number 13 is simply, go ahead and run chunk number 13. We're simply looking at one of the constants that comes with the package, and this tells you the names of the preset boundary types, right? So you can see what they are. Most of these should be familiar. IRWM, that's Integrated Water Management Districts, I believe. EVT locations, I don't know what that is. But there's the congressional districts, census tracts, watersheds, that's those are places of interest, and those are all polygons. So it's all the cities, some parks are in there and other stuff. So here's something cool. The pro tip beneath there's a function that you can use. It's called AOI preset _ geom. You put in there as the argument the name of one of those preset types, and it'll return an SF object. So like a polygon layer within R, where you can see the counties, you can plot them, or anything else with those, right? So it's basically downloading copies of those boundary layers with that function, which can be helpful. Okay, so in the next example, moving on, we want to get the climate data for Kings County. So to feed that into our API request, we need to know the FIPS code for Kings County. You can't identify counties by name because unfortunately there's some duplicate counties because it covers Nevada as well. So there's some counties in Nevada that have the same names as counties in California, so therefore the name column is not unique, but the FIPS code is unique. So you have to find out the FIPS code. And there's a constant that you can use called ID AOI preset _ ID val. You can also look it up on Google or somewhere else. But the FIPS code for Kings County is 06031. Okay, so now I'm down in code chunk number 16. Go down to code chunk number 16 and go ahead and run that entire code chunk. And as you can see, what's going on here, it's real similar to the last API request, but the first function that in that string of functions is now using CA _ loc _ AOI preset. That's the function you use if you want to use one of these preset boundary layers. And you can see the arguments there that we're passing it in. What is the preset boundary layer? What is the field that we're using to identify the specific features in there? And then what is the value of that field? So that's how that works. And then you can see also in that code chunk, we are spitting back what's in our API request, and we're doing a pre-flight check. Everything looks good. Okay. The next pro tip. So far, we've only been working with API requests that query a single location. First, it was a single point, and now it's a single polygon, a single county. You can have multiple locations in your API request. And you may remember when you get the results back, that very first column is going to be the unique ID for the location feature, right? So that's how you can then join the results that you get back from CalAdapt, the climate data. You can join those back to, your spatial layer, or maybe you have other kinds of data frames where your features have a primary key or a unique value. Okay, so you can, and that's pretty normal, right? That you want to search multiple features. Okay, so chunk number 17, we're just doing plot, and we're using the local grid equals true argument, that optional argument. And you can see we're seeing the Kings County, and overlaid on top of that are the local grid cells that intersect it. So that all looks good. Looks like we got the right place. And then code chunk number 18, go down there and click run those ones. And it is going to query the CalAdapt server and send back the values. That was pretty quick. So that seems to be working. Yeah, so now we have a table of values. Code chunk 19 is simply doing some more data wrangling. You'll notice here, in addition to adding a column for degrees Fahrenheit and only selecting the one FIPS code, it's also using pivot wider. So pivot wider is a function from tidyr And that's what you use to reshape data, right? Either going from long format to a wide format or vice versa, right? So that's PyDR is your package. These are all just kind of like standard data munging functions. And then chunk number 20, you can run on there. It's another ggplot. Here we're adding a smoothing line, and that smoothing line puts a little confidence interval around the mean. So here we can see what this plot is showing us is that if you look at the code a little more closely, it's the difference between the average maximum temperature, the difference between RCP 8.5 and 4.5. It shows that as time goes on, those two emission scenarios diverge in terms of their effects on temperature data, which is well known. Okay, so questions? Oh, thank you. Somebody clarified event locations are the stations for the OPC sea level rise hour. Okay, that's good to know. I didn't say it explicitly, but the caladaptR package does not retrieve any of the location-based data sets from caladapt. It only works with the rasters and sea level rise, and I think streamflow, there might be one or two others. Those are different, they're not rasters, they are point-based. So for those ones, you will have to find another way to get them into R. Okay, let's go down to chunk number 21. We're almost done with this notebook and then we'll take a break. So you might think, oh my God, how am I gonna find out the names of all of these climate variables? Because yeah, there's a whole bunch of them, right? So there is a copy of the caladapt raster series data catalog that comes with the package. It's basically a CSV file. And if you can get to it by CA_catalog_RS. So you may have noticed all of the functions start with CA_. And then if you put that into the view function, so I'm going to highlight just that part and then hit enter. It will open up in RStudio in a new view pane that kind of looks a little bit like a spreadsheet. All of the raster layers, right? So you can see there's 949 of them. And then there's about 13 columns of metadata. You can see the units, you can see the time periods that these work for. So this is one way that you can find a data layer for your work, right? So this is a lot to scroll through, but the RStudio viewer pane, if you click that little filter button up at the top, you can then type in something, you can basically filter on one of the columns. So for example, maybe I'm interested in extreme heat. So I type in EXT in the filter box for the name column, and I can see what of the raster series have the word extreme in them. So that can help narrow it down. Or you might be interested in the net grid, I think is a new one they've got. So, or grid net, right? So there's a few grid net layers. Anyway, so you can use the filter boxes, the filter button on the viewer pane to help you find data. Now take note of the slug column, right? So the slug column, it's kind of like the primary key. It's the one field in the catalog that uniquely identifies every raster series, right? So if you can't specify the data set that you want any other way, you can always specify it by the slug. Okay, so there's a function that you can use when building your API request. If you can't use the combination of GCM and emission scenario, you can always use the slug to specify it. And I think we have an example of that coming up. Okay, so moving on. So that's one way. There is a function in the R package that will help you also search for data sets. So you can, again, search for the word snow and see which ones match. I'm here in chunk 22, so go down to code chunk number 22 and run that. And that will basically spit back that same set of metadata, in this case for a specific one specific data set, which I've entered the slug there as the search term. And so here I can see, okay, this is, basically see what it does. All right. Okay, so the last little piece here, if you look it down, so let me go ahead and save my, I've pretty much done most of the code boxes in this notebook. So I'm going to click Save, Control S, and then I'm going to click the Preview button. And when you click Control S, you might see down in your Files pane that it generates an HTML file, right, for that notebook. So that's every time you click Save, it'll render an HTML file for whichever code you've already run. And then you can use that Preview button to view it. You can also click on the HTML file and you get a nicely rendered copy of your notebook with all the code that you ran and all the results. And this is what I would recommend that you hang on to. Take note of where it lives. If you're on RStudio Cloud, you can export it, which is how, and download it. It's a self-contained HTML file. And so this is what becomes your library of working code. Okay. Okay, let's take a 5-minute break. We'll resume at 11:10 for those who aren't tired already. And what we got coming up will be 2 more notebooks. One working with for large data using SQLite databases and TIFFs. And then we'll do a quick demo of some Shiny apps. So I'm gonna pause for 5 minutes, let people catch their breath, and then we'll continue at 5 minutes. Okay, so as we get going, a couple people have in the chat window reported error message like cannot find caladaptR, right? Like the package is not installed, right? So that's what that means. The error message is a little bit cryptic because it'll say, well, it's not available for your version of R. Well, that probably means it's just not available at all the way that you're trying to run it. So the way you install caladaptR is if you go to the workshop homepage and you click on computer setup, I'm assuming the people who are having this problem are trying to install it on their laptops on RStudio desktop. It should definitely be working if you're using the VM image that I shared on RStudio Cloud. So, but if you are installing it on your laptop, then if you're on Windows, step number 1 is you need to have RTools installed, right? So make sure that's there. That's not R. It's like another setup program that you only have to install it once, but it does have to be there because you're grabbing the package from GitHub, which means you're installing it from source. And then the next thing you need to do is, if you look in the setup help page, there's a link to a script. And then this is the magic script that you should run. So what you could do is you copy this script, just copy all of these lines of code to the clipboard and then go to your R. Now I'm in RStudio Cloud, so it's a little different here. Paste them into a new script window and then run them line by line, right? So the first line here, line 14, it's defining what are the packages that we need. So in other words, you have to install some packages before you install caladaptR, right? The caladaptR package. So if you work through this script, then this is where your, this is basically the step-by-step instructions for installing the caladaptR package. Once it goes on CRAN, this will be a lot easier, right? But it's not on CRAN just yet. Okay, I will be happy to help anyone who would like to work through this or is having problems. I did have office hours yesterday to help people with installation, but I'd be happy to do them again. So just send me a message, probably by email, because I won't follow it. I won't remember the chat window after this. Okay. So the next thing we're going to do is open the next notebook, right? So notebook 1 was kind of basic querying. the second notebook. So click on NB2 large queries.rmd, and it should open up in your RStudio. This notebook is going to be similar, but here what we're going to use is we're going to look at working with SQLite, right? So this is, we're going to look at how you would handle a larger volume of data. So you can read the preamble later about like why this might be useful. But let's go ahead and come down to code chunk number 1 and go ahead and click Control-Shift-Enter or the little green run button and run all of the lines of code in code chunk number 1 together. You might wonder, well, I already did this. Why do I have to do this again? And the reason is because the way notebooks work is that they're self-contained. So even though you loaded libraries from another notebook, you still have to load them again. And this is all in the spirit of having a completely reproducible format. Okay, so what we're going to do in this notebook is we are going to download daily data for roughly 15 census or congressional districts in the LA area for like 30 years. So that's a fair bit of data, right? Daily data is always a little bit, it's 365 times more data than your annual averages, right? So go ahead and click run code chunk number 2, and we'll talk about what's going on here. So basically, it's loading in boundaries for those 15 congressional districts. Those are saved in a geo package, which is a little bit like a file geo database. It's a single file with various layers that you can throw in there. It's open source. It's loading those into R using the stread function. So now they're in R as an SF object, a simple feature data frame object. And then we're using a couple functions from tmap to make a little interactive plot, right? And you can zoom in and out and see where they are. Okay, so now let's go down to code chunk number 3 and go ahead and run all of that. This is where we're actually building the API request, right? So here, if you look at the very first function in code chunk number 3, we're using caLOC_SF. So that's the function that you should use if your geom, your location that you want to query, is actually a simple feature layer. And then the rest of it should look pretty standard. There is one thing I'll note here at the bottom, though. I didn't mention this last time. If you look at the last function that puts together this API request, it's CA_options. This is where we're specifying, we're telling it, how do we want the different grid cells, the different local grid cells to be aggregated? Because we're telling it we want one value for the whole congressional district. And if that congressional district covers like maybe 10 local grid cells, how do we want it to combine those different values? And we're telling it to use the mean. So here you could use, your standard ones, mean, max, standard deviation, and so forth. Okay, so now we've created an API request object for those 15 polygons. And again, we're getting the daily minimum and maximum temperature for 4 GCMs, 2 emission scenarios, and 30 years of data. Code chunk number 4, go ahead and run that. You should see a little map appear that shows the congressional districts with the local grid overlay. Chunk number 5, go ahead and run that. We're just doing a quick little pre-flight check. Everything looks good. Come now down to chunk number 6 and go ahead and run chunk number 6. Now, if all goes well, this should be really quick, because normally if you hadn't downloaded this already, it would probably take like 5 to 10 minutes to download all of these data. But there's actually an SQLite database that's already inside that data folder that it's pointing to. So hopefully it should have gone really quick for you. Meaning, because what happens is if it detects that the API request has already been done and it's in that SQLite database, it'll just skip it and go to the next one. So this is how that CA getVals_DB function works, right? So you have to tell it, in addition to the API request, you have to feed it the name of the SQLite database file, which is a single file. You can name it anything you want. Conventionally, the extension is SQLite or .db. And then you also have to tell it a table name that you want it to create inside that SQLite database to hold it. There's a lot more to this function as well. You can set up lookup tables and specify indices. Won't go into any of those details, but you can look at the vignette if you're interested. Chunk number 7, go ahead and run that. And we're just taking a preview of some of the data in there. Again, so what we have now here is a remote tibble. It kind of looks like a regular tibble, but it's actually, if you look at how much memory it's consuming, it's 0. It doesn't have any, there's nothing in memory. It only retrieves data and brings it into R when needed. So that's how remote tibbles work. They're pretty cool. If you run chunk number 8, go ahead and click down there. We're using the a dplyr function called count to see how many rows are in this tibble. And it looks like there's 2.6 million rows, right? So that's not huge data, but it's nothing to sneeze at. Okay, so now we have 2.8 million values. And again, this is daily temperature data for 15 congressional districts times 4 GCMs times 2 scenarios. So it adds up. Chunk number 9, if you run those 2 functions in chunk number 9, what you'll see is that they're not very helpful, right? So this is because this is a remote tibble. It's not a standard data frame. So nrow and dim, those are the standard functions that you might use on a data frame or a tibble. They don't work for remote tibbles, right? So there's a few things that you have to know about working with remote tibbles. In general, if you use tidyverse functions with remote tibbles, that usually works fine. So for example, go down to chunk number 10 and run that. These are all standard tidyverse functions, filter, group by, summarize. This is the stuff we do in tidyverse all the time. And it works, right? You run it and you get back what you expect. We're getting a summary. It's grouping the rows by scenario, GCM, climate variable, and then giving us the mean temperature. Under the hood, what dbplyr is doing is constructing an SQL expression out of your dplyr statement. So it works for simple stuff, but if you need to go bigger than that, or you have like a more complicated pipeline of data wrangling, then either you need to go in and type the SQL by hand, which I don't recommend, or you can use the collect function and convert your remote tibble into an in-memory tibble, right? So be cautious about that. If you have like hundreds of millions of rows, that's probably not going to work, but that's how you can do it. So chunk number 11, if you come down there, run all of those. I'm not going to go through the details, but as you can see, basically, you'll see there's that collect function that's tacked on to the end of the first dplyr sentence. And that's getting those results and turning them into a regular tibble, which we need to do in this case because below that we're using pivot wider, which you can't use pivot wider on I don't think you can use pivot wider on a remote tibble. Right? That's getting into the weeds, but the take home message is if you need to work with large data sets, it can be done. Okay? You may have to learn a little bit of how to work with remote tibbles. Okay, let's go down to chunk number 13. We're creating another API request here, and we're doing our standard pre-flight checks, and we're going to plot it. This is for the Sierra climate region. So if you look at the map that pops up, this is a pretty big area, right? So this would be a lot to try to query, but what we're going to do here is get a TIFF for this area that covers this area, right? So we've created our API request object in chunk 13. And what are we getting here? We're getting, oh, this is LIVNI data, right? So the LIVNI, that's one of the data sets, and it's observed historical observations. What we're getting here is PR, so that's precipitation for 1970 to 2010, and we're getting it by year. So you might notice when you look at the API request object, there is no GCM, there is no scenario. Those aren't relevant for LIVNI data. LIVNI is observed data, it's not modeled, right? So the take home point is that depending what kind of data you're trying to pull, the functions that you're going to mix and match in your API request object are going to change a little bit. Right? Okay, so that all looks good. So now come down to chunk number 14, and this is actually going to fetch the TIFF for that area and stick it into a directory, right? And the directory is going to go into the data directory. You'll notice it also checks to see if that TIFF has already been downloaded, and if it does, it's not going to get it again, right? Because we're saying overwrite equals to false. Okay, so now we have a TIFF. Now in this case, we're just downloading one TIFF. Another API request, you could have like dozens or hundreds of TIFFs, that are needed. Like let's say you're getting modeled climate data as TIFFs. You would get one TIFF for every GCM and scenario combo, right? So that can add up. In this case, it's just one. So in chunk 15, it's actually, here what we're doing is we're reading those TIFFs back into R, and they're coming in. So go ahead and run chunk number 15, and it's bringing them in not as raster objects, but as a stars object. Because raster objects, the rasters package is maybe what you're familiar with. It's kind of limited when it comes to higher dimensional spatiotemporal data, which is why we're using the stars package here. Stars package, that's a whole nother can of worms there. It's really powerful though. It takes a lot of getting used to. If you run chunk number 16, you'll see some examples. One of the cool things about the stars package is that it's also tidyverse friendly, meaning you can use functions like slice to specify what layers, in this case, layers represent years that you want to pull out, in this case for plotting, right? And so on and so forth. Okay, so let's stop there. And in the last 10 minutes, let's look at the next last notebook, which is Shiny, which is pretty cool. Okay, so go ahead and you go ahead and save notebook 2. And so that HTML file will get generated. But as soon as that's done, open up notebook 3, which is just kind of going to throw up a couple Shiny apps like we saw one before. So I mentioned earlier, there's an R package where all of these, that has a handful of Shiny apps that I've put together. So run chunk number 1, and it's just simply loading that caladaptR apps package. That caladaptR apps package, it's a regular R package. It only has one function though, and that function is CA_launch. And then what you do is, so under, there's one line 20 in this notebook, it's commented out. So you have to remove the comment or highlight it and then hit Control Enter to run that line. And basically what that's going to do, I don't know if this is showing up on my screen share. I'll open it up in the browser. But basically this is opening up a Shiny app on your computer. And in the background, this web page that we're looking at is connected to the R that you're running, right? So in this particular one, you click on the map, you can change your, you can do all of the GCMs if you want. You can see there's some ensemble models there. Pick your mission scenario, and then scroll down and click the Fetch Data and Plot button. You'll see a little spinner going down there in the corner, and it's fetching, in this case, annual data for all of those GCMs. It went pretty quick for me, and just throws them up in a plot. Right, so that's a simple example of a Shiny app. If you're interested in seeing, well, like, how do I make that myself? I want some of that. If you go in your workshop folder, go out of notebooks, go up one level, and then click on Shiny. And then there's a couple .r files. So these are basically R scripts. And click on one of those. Click on the one that's, I'm going to open the one that says app_done. This is a fully functioning, complete app that defines both, the GUI as well as the server functions that power that GUI in R. So this is what it looks like. And this might be a little intimidating if you haven't done this before. It does take some getting used to, but the point is you can learn this if you want. It's a great way to create lightweight decision support tools for yourself and your users. And if you want to learn more, there's lots of good tutorials on using Shiny, and I'd be happy to talk to you further about how to use caladaptR in the Shiny package. The caladaptR package is Shiny friendly in the sense that there's a little progress bar that's already ready to go. And you can see some examples of that, some of the demo apps. Okay, I'm going to stop there. I want to respect people's time and end at 11:30, like I said we would. But hopefully that gives you a little bit of flavor of what you can do with the caladaptR package and what you can do with climate data in R. I mean, really, like the sky's the limit. Like if you can think of it, we can do it. Not just in Python. All of this stuff you can probably do it in Python as well. R is a pretty good platform for this kind of work. So I will stop there. I will hang on for 15 minutes or so for people who want to linger and chat or have problems with setup. But otherwise, thank you for coming to the workshop.